Barnava, Bangalore, India, right now. And Dr. Gupta will be uh, teaching a course on the core simulation of microgrids and GFM and GFL. So I welcome Dr. Gupta to start with her course, and please, the floor is yours. You can start with the course.
Yeah, thank you so much, Pasu, for the introduction. Yeah, we'll present my screen first. Uh, so my screen is visible. Let me show that.
Yeah, it's coming
Yes,
in. Yeah.
Yeah, so let me give me my brief introduction for that. So did that I'm going to present. My name is Sonam Gupta, and I have completed my PhD December 2024, and after that I have joined as a research engineer in ARCG Varnova, and I have done my this PhD under Dr. Anup Shukla and the Adrit Lab, and I have lot of good experience and memories in the Adrit Lab as well. So today I'm going to talk on my PhD work, which is on the grid connected DFIG driven wind turbine integrated with the battery storage system. So this topic is aligning with the Gyan course also, which is mainly talking on the cyber physical security, especially related to the distributed integration of the distributed energy resources to the grid. So this one topic is mainly related to what are the challenges we are facing with the integration of distributed energy resources, and mainly focusing on the DFIG wind turbines and the battery storage system, which are now placing or taking a huge place in the latest market. So the main table of the content of this presentation or this talk is on basic overview of the wind in the global, and the challenges with the wind integration, the different grid codes, especially the low voltage ride through, and its integration, this DFIG integration with the battery storage system, then different responses that right now we are looking into grid following and the grid forming, then the DFIG wind integration with grid forming battery storage systems, and other the main content of this topic is the hardware validation within the lab testing facility, either a hardware in the loop testing or the co-simulation platform for the validation or for assuring uh, the control strategy in the control strategy that we are going to propose. So first, if we look into the direct overview of this energy installation and look into the report, this global wind energy installation capacity, and out of these 20 global wind power markets, the India is ranked at third position, and it has to be grow by 9% to 2030. So that means there is a huge a place for wind and solar as well in this global market for this energy installation, and also for the system reliability as well as sustainability. If we look into the renewable energy in India, so solar is having the installation of 55%, and wind is with the installation of the 33%. That is as of 31st December this 2023. And if we look into the state-wise wind energy installation in India, so out of out of these different states, 7 states are placing or outperforming in case of the wind energy installation, and that also depend upon at what height the installation is, like 100-meter height or 120-meter height. And if we look into this, the Gujarat is having the higher installation, 84.53 gigawatt at 100-meter of height of wind turbine, and 142.56 gigawatt of installation at 120-meter height. So here the main concern is what are the challenges associated when we are integrating the wind turbines or other distributed energy resources into the grid. So as we know that the renewable penetration is increasing, especially this wind and the solar, which is also crucial for sustainability and reliability, but it is more associated with the challenges of the grid stability, and the certain challenges that we are facing with the grid integration into the grid network is its incapability of injecting the reactive power to the grid. And the main is the system stability, voltage control, Then the main issue with the reserve management and issues during the power imbalance, and the most important is the operation at the time of the grid, um, uh, challenges with the grid synchronization or operation in the islanded or the standalone mode operation. So here comes the energy storage system also, and the other advanced method that will ensure the system reliability as well. And if we look into the system stability, then out of different grid codes, then one of the main grid code requirement is the low voltage right through requirement that will ensure that the wind turbines remains connected during faults to prevent the blackouts. And if we go to the microgrid point of view, then it needs also some robust control strategies to enhance stability and also reduce the conventional sources of power for the standalone or the islanded mode of operation, so that we can reduce the cost as well as we can also reduce the reliance on the conventional or the traditional resources, that is depending upon the fossil fuel as well. So here, first we will talk on this low voltage right through. What is this low voltage right through? This is one of the grid code that need to be that is required for the wind turbines to remain connected to the grid and provide reactive power to restore voltage after faults. So the LVRT different characteristics are the voltage and the current characteristics. According to these characteristics are presenting like if the fault this fault is instant will remain for 625 milliseconds, then it will take around 1 or 2 seconds to ride through that fault. And in case till that time, if it is not able to ride through that fault, then it will get disconnected from the grid, and this will impact the stability of the grid as well. So there are to just according to this grid code requirements. So we are having the different techniques for this improvement or for maintaining this low voltage right through. One is the protection based techniques, other reactive power injection based techniques, and the other is the internal current and control based techniques. So within the protection based techniques, the different external devices are integrated into the network to assure the protection of the network, but they are not relying on the controlling or maintaining the voltages. They are
Second is the reactive power injection based techniques, where we are using the auxiliary means of supply or the external devices, so that we can, during the faults, it can come into action and will make will maintain the voltage as well as frequency, and also restore that faults, and make sure that these distributed energy sources or the wind turbines that will remain connected to the grid. And the internal control based techniques are the different controls which are implemented within the controls, because these are the power electronic based devices, and they have the capabilities of controlling through their controls as well. So LVRT requirement ensure this continuous connection of generating plant to the grid, and here our main focus is on the integration or improvement through reactive power injection based technique, which is the energy storage device. And out of these energy storage devices, we are having the different devices like battery energy, this magnetic energy resources, flywheels, and the supercapacitor. Here our main focus is on the battery energy storage system right now, because with the integration of these renewable resources, batteries are coming into action, and in case if they are also integrated into the network or the grid, then we can use the capability of this battery energy storage system not only for the power balancing or for the frequency maintenance, that these can also be used for the voltage control or for the reactive power management as well. So here, I'm not going to the basics of the this DFIG or its modeling. We'll directly go to the integration and the basic schematic or representation of the double-fed induction generator, which is integrated with the grid battery storage system. So here the main concern, as I have already mentioned about the different challenges with the grid integration. So one main challenge is the stability. And what are the reasons for this reducing the stability or stability in the network are the unsymmetrical, symmetrical fault, or the grid transients. And grid transients can be the voltage dips, or the line to line fault, or any kind of the fault. So here our main concern is, in case if the voltage will dip at the point of common connection, then what will happen to the wind turbines? That will automatically lose its synchronization. So here the battery energy storage systems which are integrated to the network, so that it will not be uh, these are integrated into the network. Here our main concern is, in case if the battery storage system or the battery banks that are already existing in the network, then we can, instead of the internal controls, that will also compromise with the active power requirement. So instead of that, we can also utilize the battery storage system for that short duration of the time, uh, to provide the essential power support at that point of common coupling whenever there are significant voltage dips. So, and this will also ensure the LVRT compliance, and automatically it will enhance the system resilience as well as the reliability. So in case here in this challenge, we proposed a coordinated control scheme. As you can see here in the schematic diagram, within the DFIG, it is from the stator side, it is directly connected to the grid, and from the rotor side, there are there are back-to-back converters which are capable of the controlling. So here the main concern is the rotor side converter control and the grid side converter control. Rotor side converter control is responsible for the controlling of the speed as well as for the reactive power management of this DFIG. And battery is also connected to the grid via this voltage source converter, which is line side converters. So here our main concern is, why not to coordinate in between these two converters, so that at the time of the fault, the reactive power will be managed from both the capabilities of the both the converter capability from the DFIG as well as from the battery storage system. So here, this coordinated control scheme that will involve the dynamic adjustment of this power set point within the outer loop in response to changes in voltage and the frequency of point of common coupling. And this seamless plug and play functionality between the converters of DFIG and this grid battery storage system, that provides a or plays a crucial role in grid management during the contingencies by providing voltage and the frequency support. And along with this simulation platform, or we have first developed the simulation for this coordinated control. Then to ensure the validity of this control coordination, then we have tested it in the with the this help of this hardware in loop testing, with the real-time simulators and whatever the facilities we have in the Adrit lab. So this hardware in loop test bench that consists of this RTDS and with battery storage system, as well as the DFIG 2.2 kilowatt of the WFID induction generator hardware prototype. And we have also validated with the facility of this hardware in loop system, this coordinated control scheme. So this is the proposed coordinated control strategy. As you can see in the right hand side, there is a DFIG control, which is the basic conventional control that we can use, rotor side control and the grid side control. And in case of the rotor side control, if we will see, we here the outer loop here is the reactive power control loop, and it is taking the reference with respect to the change in the voltage. And similarly, in case of the right hand side, there is a control of the grid battery storage system. So here the control is, we are mainly focusing on the line side converter control and the rotor side converter control of the DFIG. So here the line side control, here we can see the reactive power control is also there, and which is also depending upon the change in the voltage at the point of the common coupling. So whenever there will be a change in the voltage at the point of common coupling, and it will increase to the target value, then accordingly the mode of operation will be changed for the this battery storage converter and for the DFIG control. Because under the normal condition, this reactive power is managed by the rotor side control of the DFIG. And but in case of the in case of the faults, or in case of the severe faults, then the battery will come into the action. Initially it is working in a normal mode, like a charging or the discharging mode, depends upon the load or depend upon the present scenario. But in case of the change in the voltage, then it will automatically start supplying the reactive power and will contribute to the this voltage improvement at the point of common coupling during the faults. So this table is basically representing how this mode of operation are work during the voltage dip. We can see from here, during the 0 to 10 to 20% of the voltage, the grid side converter is working in the charging mode. So it is operating under a normal condition. But once the voltage dip increased to 30%, then the reactive power injection from the rotor side converter, that has not that is not enough to increase the voltage level. So in that case, what will happen, the grid battery storage system, it will come into the discharging mode, and it will start providing the reactive power and help in the maintaining the voltage at the PCC. So this flow chart of operation mode of the DFIG and the grid battery storage system, that is representing what is happening during the change in the voltage, like voltage at the PCC, if it is greater than 0.85, according to the this requirements or conditions, and grid frequency is less than the grid minimum frequency. So what is happening here, it is only the DFIG is come into action, only the rotor side converter and the grid side converter as well, both are coming into action for the reactive power maintenance. But once the voltage at the PCC that will come in between, uh, that will be less than 70%. In that case, the grid battery storage system, depends upon the state of its present state of the charge, then it will also start providing the reactive power, the battery reactive power, this reference that will change according to the change in the voltage. So this is how this seamless plug and play operation or the coordinated control worked for this integrated battery storage system with the DFIG for the voltage dips up to 70% or the 80%. So initially we have validated it in the simulation, and we have the simulation results that we have compared with other technologies as well. And here we have seen that without grid battery storage systems, the voltage is all at the time of the voltage dip of 50%. So there will be some transients, and also also there is a change in the DC link voltage as well. But once the grid battery storage systems come into action, and in that case the voltage will there we have seen the improvement in the voltage as well, at the time of the 50%, 30% as well. Then compared on the this right hand side, we have compared with different techniques like energy storage system when it is integrated on the DC link, because there are two ways of integrating the battery storage system, either at the point of the common coupling, like AC integration or the DC integration. So we have checked on the DC integration as well as AC integration. So AC integration at the PCC, the response is comparative better as compared to the existing one. So the next is the validation of this control strategy into the hardware in loop testing within the Adrit lab. As we can see here, this one is the lab facility we have in the Adrit lab. So this is the RTDS, which is connected to the power amplifier, or we'll first explain through this schematic representation. So how we have performed this hardware in loop testing. Hardware in loop testing, basically what we did is we have the DFIG hardware setup and as well as the battery storage setup. So we need to validate the control strategy, whatever we have implemented, that is on the hardware, whether it will work on the hardware at the time of the faults or not. So here the network through which we are going to connect this hardware with, it is simulated within the RTDS, and then with one of the bus which is in the RSCAD or RTDS, that will be scaled down to the level as per the this GTO cards, and because we have to take out the signals, and that will be taken to the power amplifier, because power amplifier, to emulate the fault conditions we need some virtual grid, and for that the power amplifier, it is acting as a virtual grid here. It is next connected to the um, connected to one of the bus, which is connected to this DFIG battery storage system, as well as the battery storage DFIG and the battery storage system. Here what we have done is, this battery is connected to one of the bus which is simulated within the network, and we are testing only on the DFIG whether it is able to remain synchronized to the network or not at the time of the 30% or the 50% of the fault. And if we look into the right hand side here, um, this one is representing the DFIG, which is connected to the DC motor. Here we are not exactly connecting to the real wind turbine. So DC motor here is acting as a emulated wind turbine, which is connected to the rotor side. This is the converter which is connected on the line side, grid side converter, and other on the rotor side, which is the rotor side converter, and one drive for the DC motor, which is acting as an emulator DC motor. And here we have the battery setup, which is again connected via DC-DC converter, as well as the grid side converters, and this whole setup is connected to one bus via this power amplifier. So this is the whole setup where we have performed this hardware and loop testing. So these are the results which we have for the 50% voltage dip and the 30% voltage dip. So we have seen an a significant change here with battery storage system and without battery storage. There is a change of 0.45% of the voltage when we are having the coordinated control strategy. And there is no as such, and when we look into the frequency, there is also a change in the frequency, but not that significant. So main significant changes in the voltage. So this one is the hardware testing, which is representing like when we are not connecting the battery storage system, then what happened during the voltage dip of 30%, and when we are connecting it with the battery storage system, so how it will be able to maintain the synchronization and will remain connected and keep on supplying the power. So without battery storage system, voltage dip, DC-link voltage, DC-link voltage will drop down, and after the fault, this emulator will disconnect it from the grid. So it is also stop supplying the power. So in case if we see on with the grid battery storage system, so when with the coordinated that control strategy, so here the power will be continued supplied to the network, and the wind emulator that is also not disconnected when the battery storage system is connected here. So wind emulator continuously generating at that time. So here, the main takeaway from this particular proposed technique is that grid battery storage system that can provide the transient reactive power of around zero 0.8 per unit, and the voltage at the point of common coupling also exhibit notable improvement increase from zero 0.5 to 0.75 per unit due to this coordinated control technique. And we have the in case if anyone wants to go to the detail of this technique or more details, this one of our publication is already there in the IEEE library, that is in the early access, so they can follow that. So next is we'll talk about very just a few brief description on the grid following and the grid forming response. So conventionally we are following this grid following response, and but right now the futuristic approach is towards the grid forming response. So what is the difference between the grid forming and the grid following is the basic, we'll go to the grid forming and grid following is the grid following basically requires a strong grid, or we can say it requires this phase lock loop to synchronize, and it is also based on the current control. And if we can see from this diagram, the input to the grid following is the reference power and active and the reactive power, and here the voltage and the synchronization, it is coming from the PLL, and here the input to the PLL is the reference grid voltage. That means it is depending upon the external grid voltage reference for the synchronization. And if we look into the grid stability case, so it has a less capability of contributing into the grid stability, especially during the integration of the distributed energy resource. So here our main approach is to upgrade the response from GFL to GFM, first from the battery storage system. So here the grid forming response, if we will see here, we are just looking into the measurement of the power from the grid. Not exactly we are depending upon the grid voltage here, because here it is depending upon the voltage control mode, and it is um, more and it is depending, and it is generating the voltage reference and the synchronization angle as well. So it is basically independently generate and regulates its own voltage and the frequency, and acting as a voltage source. And it is the futuristic approach for enhancing the grid stability, especially during the with the integration of the distributed energy resources. um, so here, so next, this is the basics of the grid following and the grid forming. So there are different approaches for the grid forming, as well as like droop control, the voltage synchronous base controls, and the synchrophasor controls. So here, the our main concern is, like I talked about, the challenges. So first that we addressed is the voltage stability challenge, and the second other challenge that we are facing is the issue with the synchronization. Initially we talked about, like, whenever the fault will happen, then how to improve the voltage at the point of common coupling. So second concern is, in case if there will be a loss of grid, complete loss of the grid, or the wind turbine has to disconnect it from the grid, and then and then what will happen to the behavior or the response of the wind turbines. So that means in under the islanded or the standalone mode. So inherently they don't have the capability of running into the islanded or the standalone mode. So here, the battery storage systems can also be the auxiliary supply for making the wind turbine to run in the islanded mode or the standalone operation. So in this case, we are mainly talking about the standalone operation of the DFIG wind turbine, by enhancing the response from grid following to grid forming for the battery storage system, which is acting, or which is providing the voltage reference whenever the grid is not there, so that the supply to the loads will be maintained. So that will also ensure the LVRT compliance and boost the system reliance and the performance as well. So here the main the what we have proposed here is the standalone, first the standalone operation of the DFIG wind turbine that ensures seamless transition during the connection process of grid forming battery storage system with the DFIG. So here the main concern here is, if we are shifting from already existing methods to to the enhancement of the other behavior, like the grid forming response, it is already existing in the simulations, and we are already having the this lab facility. Then how to ensure that it will work for the prototype or for the lab experimental validation as well. So here we need the testing platform, or we have developed a novel co-simulation platform that will integrate the two different algorithms, because we are having the uh, two different co-simulation exist when we are having the two different converters or controllers. And here we are having the one RTDS controller, and other is the wavect, or we will say the FPGA controller. So both these controllers are working on the two different languages. So the co-simulation platform here we have developed, that is with a closed loop controller hardware in loop facility to seamlessly connected to controllers, and also setting up the facilities that will test the 2 kilowatt this lithium ion battery storage system, which is integrated with the DFIG battery wind turbine system and the local load, just to ensure that whether in the grid forming battery storage system, DFIG able to sustain under the islanded operation during the different scenarios or not. So this is the methodology for the DFIG converters as well as for the battery storage system converters. So here we can see on the this left hand side, this is representing the control for the WFED induction generator, and these control or the schematics or whatever the block diagrams we are representing here, this is for the this hardware controlling. So all these controls are implemented on for the hardware system. Here we can see DFIG is connected to the DC motor, and motor is controlled to a DC drive, which is acting as a wind emulator. So from stator side, it is directly connected to the grid, and from the rotor side, the two converters are there. So here the conventional or the vector controls are implemented on the rotor side and the grid side converters. Um, this DFIG rotor side converter, we can see here the two loops are here for this active and the reactive power, or for the this rotor side converter control is basically for controlling the speed and for controlling the reactive power as well. And for the grid side converter, we can see maintaining the DC link voltage, and also ensure that the voltage will remain voltage, or it will continuously work on the unity power factor by ensuring the zero reactive power management on the grid side. So here we can see the main change or here in the grid forming this battery storage systems, because we are upgrading the grid forming this control of battery storage system from grid forming to grid forming. So here the main implementation here is depends upon the virtual synchronous based control. So here what we have done is the main thing on the synchronization. So how we have made the synchronization possible for the grid forming battery storage system to the DFIG, so that it will run in the standalone mode operation. So here is the grid synchronization synchronization method, which is depending upon the virtual synchronous control based control, and along with that, this current limiting control is also implemented, and this whole control is basically implemented in the RS-CAD and for the validation of the hardware. So next come here, from these two methodologies we can see this DFIG control, it is implemented in with the MATLAB, and the second control, which is the battery storage system, it is implemented in the RS-CAD. So here comes our this platform, which is the co-simulation platform that we have set up in the Adrit lab um, for the testing and the validation of the standalone operation of grid forming battery storage system, as well as for and as well as its integration with the DFIG. So this one is the integrated co-simulation and controller hardware in loop platform. Here we can see um, these two controllers, they are co-simulated. There is a co-simulation between these two controllers, so that the signals are exchange between the two controllers, and these two controllers are then after then integrated with the hardware which is under the testing. So that means our controller is integrated with the complete hardware. So we can emulate the conditions within the RTDS, so that we can validate it for the different conditions, like change in the this load change in the load condition. Second, changes in the grid transient, as not grid transient, changes in the common connection point transient, because this one is only for the standalone operation. Here the grid is not there. So this one is the co-simulation platform, and in case if anyone is interested in working on the co-simulation platform or the controller hardware in loop platform, so we have one this early access article right now in the IEEE Explorer. So the complete details of this co-simulation platform is already there, so that can be helpful for anyone. So this second right hand side diagram, it is representing how we have integrated these two hardwares by introducing the different control layers in between, the RTDS controller and the FPGA controller layers, and how these two hardwares are integrating or interacting with each other at the time of the different grid transients. Because um, at the time of the transients, it is working under the grid forming mode, and it is basically providing the grid conditions to the battery storage system so that it will remain under the synchronization. So we have validated for the different conditions here. So this is the experimental test bed, the same experimental test bed. The only difference here is the battery storage system that we have validated for the two different type of the battery, lead acid as well as the lithium ion battery as well. And um, for this co-simulation platform as well as controller hardware in loop platform, a sequence of operation is required, because whenever we are operating or connecting any resource to the grid or any resource to the other resource, then a sequence of operation is required. It's not like that we are switching just one switch and both of the networks are both of the networks or the both of resources are getting connected together. So a sequence of operation and a check at every point is required. So this startup sequence, this flow chart is mainly representing that complete startup sequence, how we have how we can check at each point, and how to uh, ensure the proper integration of the this battery storage system with the DFIG, so that it will keep on operating under the standalone mode operation. So we are having some experimental results uh, for this co-simulation platform. The synchronization of the DFIG battery storage system with the grid forming battery storage, we can see here at this switch S2 around in between 5.6 to 5.76 seconds, because around 5 seconds will take to complete the operation, one complete the sequence. Once the sequence is complete, then the synchronization will become active. It will be enabled from 0 to 1, and after that we can see that it will start generating the reference as well. It will start supplying to the load, and will start um, at that time we can see the battery current start reducing, because the load will be connected, and the power will be supplied, and also the battery has to uh, support the DFIG operation also. So second, we have checked for the step change in the wind speed, and the other transient cases also, to ensure whether this co-simulation platform, or whether this will be validated for only one condition, or only steady state condition, or also for the transient condition as well. So we have checked it for the line to line fault, for the three phase fault conditions, and we have seen that with the change in the load, or with the at the time of the fault, uh, due to the presence of this grid forming control and its capability of providing the grid stability, so wind turbine will remain connected to the load, or connected to that point of common connection, and it definitely makes some contribution to the stability of the system as well. So from here, the main outcome is the testing results clearly show that GFM BSS makes it easier for the wind turbine to run independently and more resilient to grid disturbance. And what we have done is the effective integration of this RTDS with FPGA controller that will allow for this controller hardware in loop testing, paving the way for robust validation platform. So uh, we have this early access article in the IEEE Explorer library. So you can follow that for the detail for more details of this co-simulation integration platform. So my last topic is on the microgrid testing. Like initially we started with the single turbine testing. So after the single turbine testing, it is required to test both the behavior, the grid following and the grid forming behavior, for the microgrid testing as well. So here comes the microgrid testing, where we have considered a very small network, a CGRI network, which comprises of this 7 to 8 bus networks, and this solar, battery, diesel, and the wind turbines are connected here in the network. And here, what we have done is, or what is the main concern is, the network is connected to the grid. So that means all the distributed energy resources that is relying on the grid. And in case if we introducing a battery into the network, and if they are working in the grid forming mode, then in case the grid is not present here, then at that time this battery storage system that will start providing the reference voltage, or that will start acting as a grid, so that the when the this distributed energy resources like solar or the wind, which is connected to any of the bus in the network, that will remain connected to the network, and it will not lose its synchronization, because these both these resources are completely relying on the grid connection. And here, our main concern is what will happen under the when the grid will get disconnected. So during the standalone mode operation, this battery energy storage system that will shift from grid following mode to the grid forming mode. So here our main proposed control is on the transition from the grid following to the grid forming mode, and maintain the error-free synchronization, or error-free synchronization or error-free transition as well. So if we see here, the network, we have divided the network into the two microgrids, microgrid 1 and the microgrid 2. Microgrid 1 is representing the grid without the network, or a simple a DC network. And this microgrid 2 is representing the AC network, because it is connected to the grid. And it is also comprising of the battery storage system and the wind turbine. And other case here, it is the solar and the battery storage system. So why we have divided it into the clusters? Because in there are two approaches. One is we are controlling a single microgrid, and second is, in case if we divide a microgrid into the different clusters, then how to control that microgrids, and what is more reliable, whether just connecting, or taking this microgrid in the cluster form, and making a coordinating control, or a single microgrid. So here we have performed some experimental testing with some controller techniques for the single microgrid, as well as for the microgrid which is operating in the clusters. So there are two clusters, DC and the AC network, and both these clusters are connected via switch also. So that means, as per the requirements, as per the controlling modes or the operation, it depends whether to this microgrid is working within the cluster form, or it will work in the single microgrid. So here, we have implemented a localized autonomous controller with rule-based logic that dynamically manages the operating modes and the breaker configuration. And the other thing, if we will see in this network, um, conventionally, if the grid will not be there, then our main resource is the diesel generator. This diesel generator is the conventional way of running the microgrid in the islanded, or in the standalone mode. So here, our main concern here is how we can reduce the operating hours of diesel generator, and how we can cut the cost by automatically reducing its operating hours if battery storage system are already connecting here. And we are also upgrading the behavior or the response of the controlling as well. So this one is the microgrid operating modes. It is basically representing that localized autonomous controller, and this controller is taking every initial or every condition of the breaker, and every condition of the present condition of the battery storage system, loads, as well as the generation. On the basis of that, these modes are decided, like how to the this microgrid is working in the cluster form, or it is working in the single microgrid, and what will happen at the time of the grid connection and the grid disconnection. In case if we will see here, if it is connected to the grid, in that case, So first, it will check the state of the charge of the battery. If the battery state of charge is less than the maximum, then it will remain in the charging mode, and it will remain in the charging mode. So but in case if the state of the charge is greater than a maximum, or it will reach to the maximum condition or 80% of the charge, at that time what it will do, it will go into the discharging mode till 70% of its state of the charge, and will support the load. So how it can help? So the amount of the power that we are taking from the grid here, that can be reduced with the help of the battery storage system if we manage battery properly in the charging and the discharging mode as per the present scenarios. And in case of the islanding detection, if once the islanding will be detected, in that case what will happen, first it will check the state of the charge of the battery. If the state of the charge of battery is greater than the minimum, then it will initially it will be working on the PQ mode, that is the simply grid form following mode. Once the islanding is detected and the battery state of the charge is also greater than the minimum, or we have already set some range for that. So if it will be greater than, then it will automatically shift from the PQ mode to the grid forming mode, and it will remain into the grid forming mode till the grid will not be available, or till it will not reach to its minimum state of the charge. Once it will be reaching to its minimum state of the charge, at that time what will happen at that time, then in the extreme state conditions, we are operating the diesel. So here we are reducing that time of operation of the diesel generator, which is conventionally, which is instantly operating during the time of the islanding. But in this case, initially the battery will come into the action. Once the battery will be discharged and the islanding will remain for a longer duration, then the this diesel generator that will come into the action. And we have seen here when the microgrid is working in the clusters, like if the solar is at its high peak hours, and on the AC grid network, the load requirement is not as such, then it will start working in the clustering mode. And in case if the fault will appear in any one of the bus that is associated with one of the cluster, then it will not impact to the other cluster. That means during the fault or during the islanding, the whole network will not get impacted. Only that portion or that cluster will impacted where the fault occurs, or where the bus will get affected. So this one is the methodology. So here the main control structure that we have implemented here is on the PLL side, because the main concern here is how we are ensuring the synchronization or the error-free phase estimation, so that the transition from the grid connected to the islanded mode operation, that will be smooth. So here when the islanding is detected, it is in the grid forming mode. Otherwise it will remain in the grid following mode. And here we have implemented replace the PLL, the basic PLL, with the dual second order generalized integrated, which is integrated with the enhanced PLL. That will be implemented or implemented in this particular methodology. And here one more thing we have done here is whatever the reference frequency that we will consider or take, we will directly taking it from the grid forming control. So grid forming control is generating the voltage as well as the frequency reference, and that frequency reference will be given as one of the input to this EPLL, instead of the frequency which is coming from the enhanced PLL. So this way it will be implemented for the grid connected as well as for the when the it will be transiting from grid connected to the islanded mode operation. So these are some simulation results, how the islanding detected and the synchronization will be achieved, because there are different set of the conditions that will be required before the synchronization, like the difference in the voltage, difference in the frequency, and difference in the phase. That should be according to the according to the requirements, or according to the set values. So once that will be achieved, only after that the synchronization can be done. Otherwise it will remain in the islanded mode throughout. So these are some this simulated results when it is transiting from grid connected to the islanded mode operation. So here we have seen, if we see to the frequency and the power only, there is a smooth transition when we have implemented this proposed controls, proposed strategy. And other is it is compared with the conventional DG and the PLL. Conventionally we are using the this diesel generator and the PLL. So when we are implementing that for the transition, then what are the transitions we have seen during the during this transit mode, and how it will be removed once the proposed strategy is implemented. So these are some simulation results uh, during for the microgrid clustering operation as well. And we have checked for the fault operation, like if the fault is occurring at bus 3 in the microgrid 1, so it will impact the other microgrid also, microgrid or not. So here we can see from here, if there will be if there is a fault in one of the microgrid, then the other will remain unaffected, that will not get affected, because this pink one is representing the response during fault when it is connected, when both the microgrid clusters are connected, and when the clusters are not connected, because the setup A and B are representing in the clustering form, and other in the just a single microgrid. So we have seen a significant improvement when the microgrid keep on operating in the this clustering mode of operation. So again here, along with the simulation, we validated it with the hardware in loop test setup. Initially, we have done it for the single turbine or the single battery storage system. So here we are having the network. So how to do that in the network? Network is already we are having that real time simulation facility. So real time in the real RTTS, the network is already implemented. So with one of the bus where the battery and the wind turbine is connected, so we have replaced the simulated battery and the wind turbines along with the hardware test setup, and the same thing we have performed for the grid connected as well as the islanding mode, in case if the switch one, because this whole network is connected to the grid, if the switch one will get disconnected, then still the this wind turbine will remain connected to the that bus, or the bus will be able, or we can say in other terms that the bus will be able to maintain that voltage throughout or not. So here we have seen some positive results with the integration of this BSS1, and also along with the this integration of that coordinated control operation, or the advanced synchronization control as well. So here we have some experimental results for that. Within this grid connected mode, the power these are the powers from battery, DFIG, and the total power which is going back to the RTDS, because in the network we can see this network at this bus, the battery storage and the wind turbine is connected. So that means the total power is also representing the power coming from the battery and the this wind turbine as well. So from here what we have done is uh, this whatever it is generating, the that generating power will be fed back to the network also. So this is the RTDS. These are the RTDS signal, which are these are the power outcomes from the hardware which are sent back to the RTDS. And we have tested it for the sudden change in the load, and we have seen the impact on the grid side converter currents and impact on the network as well. So whatever the simulation results we have seen for the simulation network, so that will be validated for the hardware testing as well. So here we have seen that this proposed control strategy achieves the precise phase estimation, facilitating smooth mode transition with phase angle adjustment within zero point 0.5 second, and also enhances the microgrid cluster stability and efficiency under dynamic condition, making it viable solution for the industrial application. And here we have done two work on this, two type of work: localized autonomous controller without interfacing that communication layer, and one integration with a communication layer, that I have done one of my colleague from the Adrit lab. So he has done that this integration of that communication layer into the network. And the details, if someone is interested in working on that socket protocol and the integration of communication layer within the network for the localized autonomous controller, that then they can go through that article, this optimized operation of ACDC microgrid cluster with modified PLL and socket protocol. And if you are interested in anyone interested in the hardware in loop testing, then they can go through that enhanced stability of ACDC microgrid cluster. Both of these articles are available on the this IEEE libraries. So this is basically the whole work that I have done by staying in the Adrit lab and by utilizing its facility, and under the supervision of my supervisor, Dr. Anup Shukla. So these type of works that I have performed and gather some experience on this hardware in loop testing, as well as the co-simulation platform for validating the control strategies, um, and the whatever the simulations we are running. So thank you for your patience and for listening to this topic. So any questions you can
Yeah,
ask.
thank you. And there is two questions from Navin Bukia. Ma'am, could you find this in the search section?
Yeah, just a second.
Okay. Please take your time, ma'am. Not hurry.
I hope I was audible throughout.
Yes, you are audible. And there is questions from the or participants. Could you find? Yeah, there is. From Navin. Ma'am, just down. Yes, from Navin Bukia.
Okay, from Navi.
Yes.
You are considered only a positive sequence component for control operation. If fault is injected, negative sequence component also present can
Negative sequence component impact the stability during the fault condition. So yes, that's correct. That not only the positive sequence, the negative sequence components also come into the action. Uh, and for that islanding operation that we have considered for the negative, this negative sequence component also, and with this RTDS facility, RTDS that is capable of capturing this positive component as well as the negative sequence component. So for the detection of islanding detection, here we have considered both the components, positive as well as the negative sequence components, because that can be you can capture from the RTDS.
Okay. I think there is another questions at the just top, ma'am. Just go up. There is one question from Navin only. Yes.
Okay. Is LVRT condition is related to wind generators only? Can we meet the LVRT condition by integrating the EVs? Yes, LVRT condition is not only for the wind generations related. It is for all the distributed energy resources. So it is a condition. It is one of the grid codes that need to be met whenever we are integrating the DERs into the network. So I was particularly talking about the wind turbines. So it is for the electrical vehicles as well.
Hope Navin got his answer. Okay. And then if there is no further questions, maybe
Mm.
if anyone have questions, please raise your hand. Okay. Yeah. I think thank you very much, Dr. Sonam Gupta, for your insightful course on the microgrid core simulations and GFM, GFL. It is truly amazing, and hope this course will